I'm going to do a little lecture here on the double slit diffraction, which is going to be in the final lab. And then I will go to another video on multiple slit gratings. But this is the important concept that you're going to need to be aware of in order to work on the lab. So basically the idea here is that you have two slits, and then you have a light wave that is hitting both slits. So this is maybe the light coming out of a red laser, let's say, or a green laser. What happens when it hits the slits, and remember these are like the peaks or the crests of the wave. When they exit through the slit, they're actually going to exit in a fashion that looks like this. They're going to exit in a fashion such that it's as if each slit is a source, putting out light which is expanding then spherically, as if it were emanating from that slit right there. This is something called Huygens principle, which says that that's going to take place. But I'm just saying that because you're going to need to know that in order to figure out what's going to happen. Huygens principle basically says that when a wave comes through a narrow aperture, it expands outward as if the wave were emanating from a single light source like that. And this experiment is actually an experiment that supported the idea that light is a wave rather than a particle. Although there are other experiments that demonstrate that light has more of a particular nature to it. So, but we're going to be treating light as a wave for the reasons we talked about in another video that relates electromagnetism to optics. Okay, so I'm going to go to a new slide, but basically this is the idea. And so light is emanating in all directions from both slits. From there, in any direction, you're going to have the light coming or exiting the slit. So what we're going to do is we're actually just going to pick a couple of these directions in the next slide. Or actually, I'll draw it right here. And we're going to imagine again that we have two slits right here. And we're going to imagine a screen in the distance. So the screen's far in the distance. So this is a much, much bigger distance here. I'll call it D. Actually, I'll call that distance X rather than D. Don't remember what I call it in the lab, but for right now I'll call that X. And the spacing here is considered to be D, the spacing between the two slits. So let's look at what happens when light comes from this slit. It should be a straight line, and again, this is one of the blue arrows over here. This is this blue arrow, let's say. And then light comes from this other slit here, which is one of these blue arrows, let's say that one, and that these two portions of the expanding light from each slit meet each other at this point on a distant screen, a distance x away. What happens? Well, it really depends upon how big a difference between the distance between the light coming from this slit right here and the light coming from this slit right here. If they travel the same distance, then the light is basically going to be at a maximum and a minimum at the same physical location here at the same times, and so the two light rays will reinforce each other, kind of like a constructive interference. This should harken back a little bit to the idea of standing waves. So it's as if you get a really bright spot right here where the two lights interfere constructively so that they reinforce each other. That would result in a bright spot. If one of the light rays traveled a little bit more than the other light ray, for instance, let's say the light came over to here, and you can see this is quite exaggerated, but this light ray right here, which I'll label with the blue line, is traveling a much greater distance than the one that I'll label with the red line right here. In that case, the waves, there's a possibility that one of the waves will travel a half wavelength further than the other wave, such that when the one in the blue, let's say, is a maximum, then the one on the red is a negative of that, and that the two cancel each other out. And so that would result in a dark spot on the distant screen. So the idea is that on this screen here in the distance, along here, that you're going to have regions of bright spots, such as right in the center here, and you'll have regions of darker spots, such as this point here. And then all along you'll have alternating fringes between bright and dark spots, depending upon the geometry of the situation. Okay, so conceptually that's what's going on. And in the next slide, I will show you how to do some calculations with respect to that. Okay, so now I'm going to show you some calculations. My cat's purring on me, so if you hear any funny noises, that's my cat. Anyway, here is the situation. We have, again, we have our two slits that the light is coming from, and we have our distance screen over here, distance x away from the slits. Spacing between these slits is d. And the assumption here is that x is much, much larger than d. May not appear to be that here, but I'm showing this in an exaggerated view so that we can actually see the geometry of what's going on. So let's say I have one light ray that's going this distance here, and another light ray that's going this distance here. It's supposed to be meeting at the same point. Let me try that again for this one. So the other light ray, maybe I'll do it in reverse. From here. You're seeing a lot of mess-ups here on the drawing. One more time. There we go. Alright, so one of these light rays travels further than the other one, and our goal is to find out how much further this light ray is than this one. And I'm going to call this one R1, and this one I'm going to call R2. So I basically have to subtract two vectors. That's what's going on here. I'm interested in the difference in the distances between R1 and R2. So how do I do that? Well, if you make the assumption that x is much, much larger than d, I'll show you this in the next slide, then what you actually have is something that looks more like this. Over here, here's my two slits. There's one there, there's one there. It's really hard to draw that, but they're basically very close to each other there. And we have this big distance here. Here's my x. Here's my distance screen. And here's one of the light rays. Here's the other light ray. Hopefully you're getting a laugh out of this. Terrible drawing. It's hard to draw a straight line here. I'll learn that better next time I do this video. But basically, these two light rays right here look like they're parallel. Now they're not parallel because they meet at this distance x over here. But they're so close to parallel that we can make the assumption that they're parallel. And if we make that assumption, I'm actually going to end this video, and I'll show you on the next video what happens when we make the assumption that these two light rays are parallel. This video is long enough.